Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Viktor Gruev, and these are the students in my lab that are co-authoring this paper. I'll talk about the research efforts that are going on in my lab on high-resolution and real-time spectral polarization imaging sensing. So it's a very multidisciplinary effort, going from nanofabrications, optics. We do a lot of custom imager sensor design to the algorithms and so forth. So just before we get into the detail of some of the sensors that I'll talk about let's just take a look at it and review the polarization of light. Most of the talks that we've heard this last couple of days, you treat light as a ray. We have to look at it, think of light as a wave, as an electromagnetic wave, and just kind of a review. An electromagnetic wave is basically propagating, or a transverse electromagnetic wave is composed of two orthogonal waves, X and Y. They're propagating in space and time towards you. So whatever that ray you were thinking about, your ray tracing program, now think of it that there is actually a wave superimposed on that particular ray. When we're talking about waves, there are three fundamental properties. That is the intensity, the wavelength, and polarization. The first two are basically encoded as brightness and color by our visual system and by the imaging sensors. The actual polarization, which is the difference between the phase, as shown here, phi x and phi y, it gives rise to polarization. So if you think of it as light propagates towards you, this ray that was traveling towards you in space could be unpolarized, which means the phase difference is zero. So there's no particular kind of oscillations in this wave. Or it could be somewhat polarized. In the middle case, light could be linearly polarized with phase difference of zero. And in the later cases, what I call, this is probably the more generic polarization signatures in nature, where light is neither polarized or linearly polarized. They're sort of in between, or called partially polarized or elliptically polarized. And if you project this pattern from space into your xy plane, which is coming in a second, you're going to see that the linearly polarized light, the middle one, describes a line as it travels through space, versus the partially polarized light, it describes an ellipse. So that's why elliptically polarized light is commonly referred to partially polarized light. And random, sort of, you get these random projections. Now, if you want to learn something about polarization, capture polarization, we want to be able to describe this ellipse. And we want to describe it in terms of what is this major axis, what we call it angle of polarization, and what is the ratio between the major and minor axis, which is known as a degree of linear polarization. Now, I represented these two quantities in terms of this Stokes parameters, so you can think of them as sort of your temporary variables. And the way you can compute your Stokes parameters is by capturing the scene with 4 linearly polarized light in the linear polarization filters. In other words, I need to know what is the scene, what is the light as I filter it through a 0-degree polarization filter, 90, 45, and minus 45, and then I can tell you everything about polarization. In a nutshell, you need to sample your light field with minimum of 4 polarization filters to be able to say something about polarization. And this is how people have actually captured polarization using division of time. You rotate either a polarization filter or a retarder in front of your camera, so you're multiplexing time. It's a pretty straightforward, except you have to be very much aware that any wobbling that can happen in your rotation will actually cause serious polarization errors. A 1 arc second wobbling if your rotational retarder can cause about 1% error in your polarization measurement. And it could be somewhat random if you don't know. About 20 years ago or 15 years ago, people came up with this division of aperture, kind of where you put your polarization filters right at the aperture of your sensor. So you put multiple microlenses and polarization filters to be able to capture polarization properties. And people have been doing this thing for the visible spectrum through the midwave IR spectrum. There are a couple of other methods. In my lab, where we kind of start working on this sensor, we said, well, there is actually a great parallel from the two previous methods, how color sensors have actually evolved over time. Division of time, amplitude, aperture, and so forth. Essentially, in 1976, the Bayer pattern came around, where you integrate your color filters, 2 green, red, and blue on top of a imaging array, and gives you a really compact, robust color sensor. And this is what we use predominantly today. And this is sort of the challenge that we set ourselves. Is that can we actually create a similar sensor that would actually incorporate these polarization filters directly on top of each pixels? And one of the main challenges has been fabricating reliably this polarization filter. A polarization filter is nothing more than a fence, a bunch of lines that are in parallel, except if you want to sense polarization light in the visible spectrum, this fence has to be on the order of nanometers. Luckily, nanofabrication and technology has kind of caught up and allow us to fabricate some really small structures today. So we've been able to use interference lithography in our lab to fabricate this aluminum and other metallic wires, gold, silver, at about 70 nanometers, going down to 20 nanometers lately. And we can orient them in random orientation. And this is sort of a scanning electron microscope of the structure that sits directly on top of our pixels in our imaging sensors. If you look at under an optical microscope, our camera has, and you shine 0-degree polarized light, you can see that the 0-degree pixels are transparent, 90 degrees block light, as they should, because polarization theory tells us they should block orthogonal polarized light. So there's been kind of a lot of challenges of how to integrate this nanotechnology, nanostructure directly on the CMOS sensor. This is something that we've worked quite a bit in the last couple of years of monolithic integration of various nanostructures. And we're not just bound to these lines, we're actually experimenting with different holes, crosses, and so forth to get even spectral or additional filtering on per pixel base. The nice thing about it is now we have this high resolution, megapixel, 2 and 4 megapixel right now, pixel size of 7 microns, and sensitivity throughout the whole visible spectrum, and it's monolithically integrated. So one thing is you are capturing polarization information at every frame, which is not the case with time division polarization imaging sensors, and it's a very robust sensor. We've used the sensors from underwater to putting it on balloons, and it still gives us a very good polarization properties through here. There's just kind of an example. We didn't have a chance to see the demo this morning. This is our little trusty horse that's made out of plastic. Every time you have a reflection, light will become polarized. And it does depend the degree of polarization. So what you're seeing here is the intensity image. And on purpose, we've chose a scene where you cannot discern very much the shape of this object very much. The middle, the top right image is the degree of polarization, meaning how much light is polarized. Dark means there's no polarization information. Bright means it's highly polarized, this target. So we are rotating our polarization Macbeth chart, different linear polarization filters to kind of tell us, yes, we are supposed to get highly degree of polarization. And the angle of these filters these filters are oriented at different angles, so you get different colors. We are mapping angle of polarization to color, meaning red means light is oscillating horizontally. That ray that's entering the scene is oscillating parallel to your imaging sensor, or blue could be something that's orthogonal, that's orienting. And again, both from the grayscale image, which are the kind of two different sets of images that we're capturing, from the angle of polarization, you can see actually you are capturing the surface normal information from the sensor using at every single frame. Essentially, you're capturing without playing too much with the lighting conditions. And you're getting reliable information even down to few photons, something that you don't even capture very well, a difference between your target and the background. So people have looked at it, 3D shape reconstruction based on polarization in CVPR community using division of time, multiplexing polarization cameras. Now I think there's sort of an interesting opportunity where at every frame, essentially, you're capturing polarization. Can you couple it with the fact that you can be tracking an object and at the same time recovering its shape? And it poses some very interesting computer vision challenges as well. Now, this was about a couple of years ago, and we sort of stopped there and we said, well, you have your color sensors. They are capturing some, this is what most of the time we are kind of used to looking at information, and we've been kind of diving into the polarization world. But this sensor is actually oblivious to color. Like, how do we actually add color and polarization at the same time? So we use actually, skip to the next slide. We looked at some various imaging techniques. And there's a basic physical principle that says different wavelengths will penetrate materials at different depths. In other words, if I have blue light, majority of my light, 99% of my photons that impinge on my photodetector will get absorbed in about 2 microns in my photodetectors. Red light actually penetrates much deeper into your silicon, right? And there are actually some problems by the reason it penetrates so deep into your silicon. Versus green light, majority will actually get absorbed about 6-7 microns. So if you actually place vertically stacked photodetectors at different depths, at half a micron, micron to 2 microns, you can actually start discerning what kind of wavelengths you're getting. So we sort of fabricated our own CMOS technology, and we use commercial technology as well from Foveon. And essentially, on top of this vertically stacked photodetectors, we've deposited these nanowires. So each pixel, this 0-degree pixel, actually is able to sense red, green, and blue, actually even more spectrums. But we typically limit ourselves to red, green, and blue. And the same is the case for this neighborhood of 2x2 pixels. So now you're getting your color information on every pixel, and you look at polarization information on this superpixel. The resolution that the first generation is a VGA format, running at about 25 frames per second. We've moved to a 2 megapixel. There's a lot of data that comes out of this sensor. So getting this data into your computer is somewhat of a challenging task. So 2 megapixel at 40 frames per second, we're sort of limiting a dual band camera link interface. This is some of our images that we are able to obtain relatively recently. It's our color image sensor, McBeth chart. The colors are still not the sharpest. They do require a lot of nonlinear image processing. And you'll see why in a second. Up here, we're actually presenting degree of linear polarization. So we have our linear polarization filters that do exhibit high degree of polarization, so therefore they are red. And down here, actually, you can see them different colors because they actually reflect light that's oscillating at different angles. So we're capturing both angle and degree of polarization. The ink on the McBeth chart actually polarizes light. And depending what kind of ink they actually use to fabricate it, you get different degrees of polarization, which is kind of a known fact. Different degrees of polarization will give you this part. This is the spectral response of the camera. You're getting red, green, and blue. Your red, green, and blue are relatively broadband. And this is where it requires a lot of challenging signal processing to shape it up to look to get good color information. And up here is actually the polarization information from a neighborhood of pixels as we are changing the incident angle of polarization. I just have one kind of comment on the processing. It's actually a lot of interesting problems are coming out of this sensor. It is a unique sensor. It is sort of resembles Bayer pattern, but it does poses its own image processing challenges. So you could port calibration interpolation directly from color to polarization, but actually polarization is more mathematically constrained than your color image processing. So it does lend to some very interesting interpolation technique that we're exploring in our lab using correlation-based and calibration, which I think is essential. And we've shown actually, if you know something about the statistics of the scene, you can recover your full resolution. In this kind of sensor, you do lose some of the resolution, but with some really clever interpolation, you can actually recover most of that resolution. And lastly, one of the challenges, a lot of these sensors are used in remote sensing, a different community in the optics. The way we present data, I think, is a really lousy way. We use grayscale to present degree of polarization, and it's a really poor man's version to present data. So I think there are some interesting ways to present this data. So I'll end with this slide. We have a variety of kind of polarization imaging technology ranging from VGA format to high resolution 4 megapixel and 30 megapixel right now on polarization and spectral polarization. It's a really interesting field of merging this nanotechnology, nano structures with existing imaging technology. There are some very interesting problems that you could be solving by carefully engineering your nanostructure, whether it's spectral filters, polarization, or you can play around with many different combinations of this information. So with this, I'd like to conclude my talk. They're about 100. And by making this nanowire smaller, we're actually able to increase. I do think it's actually the reason we're getting 100 is due to optical crosstalks. You are mixing information, the same thing as in color. I think as long as you can properly model that, I do believe the extinction ratios are in order of magnitude higher, but you need to understand what's happening in the pixel neighborhood. You have both.
So if they're reflective, the energy goes back to the lens and then reflects back again.
Right. I mean, you can engineer, right? There are some angles that this is very problematic, right? Majority of it will get absorbed into the wires. Some of it does get reflected. Yeah, you do have multiple reflections in there. I think that's also one of the problems. There is an anti-reflective coating. I think it's a question. I think that also causes additional reflections. I think you can engineer these wires. If you don't have sharp edges, you can actually mitigate this problem a little bit better. Yeah. Yes?
What sort of applications are you using this for? Do you anticipate?
Right. We have a couple of different applications we're pursuing. I would say just two I will name. In the biomedical imaging, we're looking into endoscopy. We've actually shown that lesions or adenomas in the colon, you can actually detect it with polarization. What polarization actually captures is the index of refraction. So healthy cells versus cells that are somewhat questionable do have a different index of refraction. So that gives you a very good screening technique. You do have to narrow your spectral range for that application. There are a couple of remote sensing applications where man-made objects pop up very nicely in scattered environments, such as fog, haziness, underwater. So this is kind of complementary. I do have to say that in this technology, having both polarization and color is key, right? Adding the value of polarization. Polarization will give you certain benefits in some situations. So I think having both of these modalities, I think, is crucial.
Okay, let's thank our speaker one more time.
Thanks.